So it's just past 7 o'clock now. We still have a few folks joining in, and that's just fine. But we will get started with some introductions and some housekeeping. So hello, thank you so much for joining us for Energy Talks this evening. My name is Cassidy Monroe. I am a community librarian with the Edmonton Public Library, and I am very happy to be joined by Future Energy Systems on the speaker series that we've now been doing for over a year online, which is pretty exciting. Little bit of housekeeping. We will be recording the talk this evening, but we're just recording the highlighted speaker and the presentation. The caveat to that is if you want to ask a question and not be recorded, you can absolutely put it in the chat or send it to myself or Valerie, who will introduce in a moment here, and then it won't be captured on camera. The nice thing about this is it means if you have to step away or you miss anything, it will be available on Future Energy Systems YouTube in the future, so you can rewatch and check out all of the other speaker series that we've done over the last many months. The other piece I want to add is that this is one of many online speaker series and classes and events that we're doing with the Edmonton Public Library, and they are free for everyone to join wherever you are. So we already popped the link for our next energy talks, but we have talks with the Archaeology Society of Alberta, the Paleontology Department out of the U of A. We also have one coming up on women in politics that I'm really excited about here in Edmonton. So I'll make sure there's a link for that sent out. But with that, I'm going to pass it over to Valerie Miller, who is my partner with these Future Energy Talks, to do a land acknowledgement and introduce our speaker.
Thank you so much, Cassidy. Hello, everyone. My name is Valerie Miller, and I'm the Outreach and Engagement Coordinator for Future Energy Systems. Thank you so much for joining us today. First of all, the University of Alberta would like to acknowledge that we are located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. And we are so happy that you're here to join Future Energy Systems tonight to learn a bit more about geothermal energy. Future Energy Systems was launched in 2016 with a $75 million grant from the Government of Canada's Canada First Research Excellence Fund to help Canada transition to low net carbon energy economy. We focus on multidisciplinary research that develops the energy technologies of the near future, integrates them into today's infrastructure, and examines possible consequences for our society, economy, and environment. We also contribute to the development of solutions for challenges presented by the current energy system. In Future Energy Systems, we have 112 research projects, 147 researchers, and over 840 graduate students, postdoctoral fellows, and highly qualified personnel, one of whom you're going to meet tonight. One final statement on that: we wish to remind current and future viewers of this talk that the opinions expressed by the speaker are not necessarily those of the Edmonton Public Library, Future Energy Systems, or the University of Alberta. We're gonna get started right in a minute. Just for the format of the event, we'll be stopping about halfway through for questions. So you don't have to hold off. You can put them in the chat and I will ask them when we get to that pause, or you can ask them yourself, and then we'll have more questions at the end of the session. So you have an hour and a half to ask all the questions that you want. Take advantage of that. We're gonna have a great discussion this evening. And now I would love to introduce our speaker. Cedar Hannison is a PhD candidate in the Department of Physics at the University of Alberta. In 2017, he received a Bachelor of Science honors degree in geophysics from the University of Victoria, then moved to Edmonton to begin graduate studies under the supervision of geophysicist Dr. Martin Unsworth. Cedar's scientific research uses geophysics to study the rocks of southern BC, and he applies this research to the search for geothermal resources. Cedar, thank you so much for joining us tonight.
Thank you for having me, and thank you for that lovely introduction, Valerie.
And we're going to pass it over to you so you can share your screen, and we're going to get right into this.
Yeah, I would just like to clarify a term that perhaps the audience is not familiar with, which is PhD candidate. And that's just a fancy word that we use in academia for a PhD student that has passed their candidacy exam, which is kind of the major milestone roughly halfway through a PhD program. And a little bit about myself. I spent most of my life in Victoria and Greater Vancouver. And as Valerie mentioned, I got my bachelor's degree from the University of Victoria and then moved to Edmonton to study at the University of Alberta. And I use radio waves to study rocks. Yeah, Valerie already gave a wonderful acknowledgement, but I'll just show that this is Treaty 6 here, and we do very respectfully acknowledge the traditional lands that we are situated on. So an overview of the next hour or so. We will start with an introduction. I will talk a little bit I will talk a little bit about what the inside of the Earth looks like and why it's hot. And then I will teach you the basics of plate tectonics, stuff like subduction zones and volcanoes. And then we'll dive into geothermal energy for the bulk of the first section. What is geothermal, who uses it, why should we use it, the difference between electricity and heat, and then I will kind of do an overview of a few of the major groundbreaking projects currently underway in Western Canada. After this, we will take a short break to stretch your legs and answer some questions, and then we'll come back for the second half of the talk, which will be about geophysics and my research using radio waves, specifically at a volcano in BC. And then I'll finish off the talk talking about green hydrogen. And so as advertised, you hopefully will know a bit about hot rocks and radio waves by the end of tonight's event. So at the beginning of the Earth, shortly after it formed, so about 4.6 to 4 billion years ago, the Earth was extremely hot, as shown in this artist's rendition at the bottom. This was due in part because there was lots of radioactive elements that give off a lot of heat, and it was also constantly getting bombarded by rocks from space. In 1862, Lord Kelvin tried to use a basic simple cooling model to estimate how Earth the old was, but he didn't take this radioactive decay into account, primarily because it hadn't even been discovered yet. And he estimated that the Earth was only 20 to 400 million years old. We now know that it is much older than that, more than 4 billion years old, and it is still cooling down 4 billion years later. Some of you may have seen like a cartoon like this, what the inside of the Earth looks like. The Earth has a thin crust on the outside that's less than 100 kilometers thick. And then there's a mantle that's about 2,800 kilometers thick. And then a liquid outer core that's about 2,200 kilometers thick. And then a solid inner core with a radius of about 1,300 kilometers. So in total, the Earth has a radius of about 6,400 kilometers. And heat is transferred within the Earth by convection in the mantle and the liquid outer core. So convection is how you would heat, say, a pot of soup, where the fluid actually moves around. And then the solid parts of the Earth, heat is transferred by conduction. And so that would be if you had an electric stove heating up the bottom of your pot. Just by direct contact. So that's heat conduction. And then, as I mentioned on the last slide, heat is generated inside of the Earth by radioactive decay, specifically of uranium, thorium, and potassium. So the Earth is constantly creating more heat. About 3/4 of the heat that leaves the surface of the Earth is due to this radioactive decay. Only a quarter is because the Earth is cooling down from that heat 4 billion years ago. 99% of the Earth is hotter than 1,000 degrees, and the center of the Earth is about 6,700 degrees, which is hotter than the surface of the sun. Of course, we can't access most of the Earth, The deepest that humans have ever drilled is about 12 kilometers. And typically we only drill several kilometers, primarily because drilling costs about $1 million per kilometer. And the deeper you go, the more expensive it gets. I think this really deep well, by the time they were done, they were up to 3 or 4 million per kilometer. So for the rest of the talk, we're just going to think about where humans can actually get to. And so that's the crust. So the Earth's crust is made up of tectonic plates. As you probably know, there are 7 major plates: North America, South America, Europe, Africa, Australia, Antarctica, and then the Pacific, as well as dozens of smaller plates. And the boundaries between these tectonic plates are where most of the Earth's volcanoes and earthquakes occur. You probably have heard of what we call the Ring of Fire around the Pacific plate, where there's lots of earthquakes and volcanoes. Offshore southwestern Canada and northwestern United States, the Juan Defeca plate, this little plate here, is subducting beneath the North American plate. And so what happens is magma comes up to the surface from deeper within the Earth and creates new ocean floor at the Juan Defeca Ridge. And then the Pacific plate moves away and the Juan Defeca plate moves away from this zone of new Earth creation. And then at the Cascadia subduction zone, the Juan Defeca plate goes down into the Earth and goes underneath the North American plate. And as it goes down, it takes water with it. The sediments are wet, and there's also hydrous minerals in the rocks. And when it gets down to a certain depth and pressure, water is released, and this causes the North American plate to melt, and magma rises to the surface and erupts to cause volcanoes, for example, Mount St. Helens here. And so there's a chain of volcanoes that runs from BC all the way down to Northern California called the Cascadia Volcanic Arc. And the northern segment of the Cascade Volcanic Arc is called the Garibaldi Volcanic Belt. It goes from Glacier Peak in northern Washington all the way up into central BC. And in Canada, in this the Canadian segment of this volcanic arc, the most recent volcanic eruption occurred at Mount Meager, and this is one of the areas I study for my PhD, and we'll be talking about it during the second half of the presentation. So the Garibaldi Volcanic Belt is part of the Coast Range in Western British Columbia. And inland from there, we have the Columbia Mountains and the Rocky Mountains. And then to the east of the Rocky Mountains is the Western Canada Sedimentary Basin. And this geologic feature covers much of the prairies, and it contains most of our country's oil and gas resources. In this kind of cross-section cartoon across the basin, you see that there's the Rocky Mountains, and then the Western Canada Sedimentary Basin, and then the Canadian Shield. The Western Canada Sedimentary Basin is made up of layers of sedimentary rock, and these layers trap oil and gas. And more than 500,000 oil and gas wells have been drilled in Alberta, and more than 100,000 in Saskatchewan. These wells have provided a wealth of geological data, and we know that in addition to these layers holding oil and gas resources, they also hold a lot of hot water. A key thing to think about and know about when you're studying geothermal is something called the geothermal gradient. So if on average the surface of the Earth is 5 degrees and the center of the Earth is 6,700 degrees, then it must get hotter as you get deeper. And that's exactly what happens. So in the Western Canada Sedimentary Basin, on average, If you go down a kilometer, it's about 45 degrees. If you go down 2 kilometers, it's about 75 degrees or so. 3 kilometers, you're up over 100. And then by the time you get down 3.5 kilometers, you're at about 120 degrees. And this is important to keep in mind because to generate electricity from hot water, it needs to be around 120 degrees. And this geothermal gradient is not uniform. This is an average. So some parts of the sedimentary basin shown in red and yellow, it gets hotter faster as you go down than other places in blue and green. It'll get hotter more slowly. So for reference, here's Edmonton. So who uses geothermal? Currently, the United States is the world's largest producer of geothermal electricity. And as of now, Canada does not send any electricity to the grid from geothermal power plants. In Canada, the best place to look for geothermal or to try and do geothermal is in the West, Saskatchewan, Alberta, BC, and the territories. This map is showing how much heat leaves the surface of the Earth. So red and orange means lots of heat is leaving the surface of the Earth, and blue and green means not very much. So we definitely are interested in Western Canada for geothermal energy. Why should we use geothermal or any renewables for that matter? Well, the current energy system is a leading cause of climate change, and the public is becoming increasingly concerned about this. Carbon dioxide is one of the main greenhouse gases in the Earth's atmosphere. And what it does is it traps heat that would otherwise escape into space, much like a greenhouse. And since the 1950s, it has been above 300 parts per million, which is more than it has been during the previous 800,000 years. By the time I was born, it was up to 339. By the time I was a teenager, 358. And then it just kept rising, and we're well over 400 now. And this increase in CO2 is a major driver of climate change. And the burning of fossil fuels adds CO2 to the atmosphere. And so if we want to slow the progress of climate change, we need to reduce emissions of carbon dioxide and other greenhouse gases, and ideally also sequester greenhouse gases by pulling them out of the atmosphere. Canada's energy consumption is still dominated by fossil fuels. In 2018, the majority of our energy consumption was from natural gas, petroleum, and other fossil fuel liquids. Canada has committed to reducing its annual greenhouse gas emissions to 60% of 2005 levels by 2030, and then net zero by 2050. Alberta has made its own commitments regarding methane, which is another greenhouse gas that results from the oil and gas industry. And they've committed to cleaning up our coal-fired industry as well. So these governmental mandates on a provincial and a federal level is driving a desire to diversify our energy portfolio. So in 2018, 16% of Canada's energy supply was from renewable sources, and about 2/3 of that was from hydro. In recent years, we've seen wind and solar increase. So this big dark green area is hydro. It's increased a little bit over the past decade, but the wind and solar are really ramping up. But currently we don't use geothermal. And unlike wind and solar, geothermal can provide something that we call base load electricity. And all this means is that it's consistent, it's constant. Geothermal can provide the same amount of electricity day or night, all year long. Whereas, as you can probably imagine, wind and solar varies throughout the day, throughout the year. And so this is one of the big advantages of geothermal. So how do we turn that heat inside the Earth into electricity? So this little cartoon, that's not to scale, obviously. You drill a few kilometers into the Earth, and then you bring hot water up from the depth, the deep earth, and then you use steam to drive a turbine and a generator and produce electricity. And then you inject the cool water back into the earth where it can heat up again and you can pump out more hot water. There are three main types of geothermal power plant. The first one is called flash steam. For this, you need very hot water, generally hotter than 180 degrees. It's under pressure, and you don't need to pump it to the surface. It basically spontaneously boils, and you use that steam to drive a turbine. A binary cycle power plant is by far the most common, and this is what we're likely to see in Canada. You need hot water between 100 and 180 degrees. Typically, the target temperature is between 120 and maybe 130 or 140 degrees. And so this hot water is pumped to the surface, and then you use that to boil a secondary fluid. So you're not using water steam to run your turbine. You're using what they call a working fluid to do this power generation. And then the third is the least common. It's where you actually drill into a pocket of underground steam. I'm not sure if we have any of this in Canada, but the United States, as far as I know, only has one power plant that does this. So it's not very common. And I will just amend this slide quickly and say that hot water is usually taken from the underground reservoir, and that these are the three different types of conventional geothermal power plant. Because in 2020, Green Fire Energy in California and Calgary-based Ever Technologies in Alberta both demonstrated that you can use what's called a closed loop system, where you have a working fluid and you send it down into the earth, it heats up and then comes back and then just keeps going around in a closed loop. So you're not actually bringing hot water up from the surface, you're just circulating a fluid through the hot rocks, through a generator, through the hot rocks, through the generator. So I won't be speaking any more about this. This is an emerging technology, something to keep your eyes on, and something to be excited about here in Alberta. So in addition to using heat to generate electricity, we can just use that heat directly. And so the main use is called district heating, where you use hot water from underground, again, to heat a working fluid, and then that fluid goes and heats buildings. So this is particularly appealing in the cold parts of Canada, because you don't need boiling water. You just need the water to be hotter than the ambient temperature, which can be quite cold in some parts of Canada. In addition to heating buildings, you can also use this heat for agriculture and aquaculture, things like fish farms, greenhouses, crop drying, composting, all kinds of things that we normally use electricity or gas or whatever for, we could use geothermal heat. You can also heat swimming pools or have artificial hot springs for tourism and stuff like that. And you can also melt snow and ice off of roads and sidewalks, which saves money on like plowing and stuff like that. Also, the last thing I want to mention is heat pumps or heat exchangers, which some of you may have heard of, or some of you may have even had in your homes. So a heat pump transfers heat from the ground to heat your house in the winter, and most of them are a two-way system where you can also transfer heat from your house to the ground to cool it down in the summer. And these basically work the same way that an air conditioner or a fridge or a freezer does. And a refrigerant evaporates from a liquid to a gas if you want to cool your house down. and that same refrigerant will be condensed from a gas to a liquid to provide heating. So this is a very appealing way. There's an upfront cost involved, but it's in the long term, it's an efficient way to heat and cool your house. I just wanted to mention that the heat source for a heat pump is quite shallow. So it's very different from geothermal drilling where you're going kilometers into the earth. Now I want to talk about some of the big projects currently underway in Canada. Let's start here at home in Alberta. There's a project called Alberta number 1, about 20 kilometers south of Grand Prairie. For those of you not from the area, that's about 400 kilometers northwest of Edmonton. And it is led by an Edmonton-based company called Terrapin Geothermics. And they're hoping to drill down to less than 4.5 kilometers and get that 120-degree hot water that is necessary for running a geothermal power plant. And this is some data of temperature as a function of depth near where they're setting up their plant. And this is to illustrate that wealth of information that we've managed to get from decades of oil and gas exploration. And it's shown that if you go down 4 kilometers, you'll probably get to the required temperature. So they plan to drill 5 wells, 3 for bringing hot water to the surface, and then 2 for putting cool water back into the earth. And they expect it to produce 5 to 10 megawatts of electricity using a binary cycle power plant. So that's that second option that we were talking about, where they will use the hot water to boil a secondary fluid. To give you an idea of what like megawatts are, 5 to 10 megawatts is enough to power approximately 7,000 average homes in Alberta. However, this facility will be used to provide electricity and district heating to nearby light industrial facilities. And in 2019, as part of the federal government's push towards renewable energies, they received a $25.5 million grant from NRCan. So let's look a bit of the news. Back in March, they took a temperature log in an old well, and they found a temperature of 118 degrees at a depth below 4 kilometers. And so this shows that it is economic for them to set up a power plant in this location. And then about a month ago, they just announced a agreement that they've come with. And so they're going to use some of the heat from this geothermal plant for industrial vermicomposting. So that's one of those additional kind of value added things that you can use the heat for. So that's really great to see. Now let's move next door to Saskatchewan. There's a project just down by the US border, southwest of Estevan, Saskatchewan, called DEEP. And this project is already underway. They have already drilled the deepest well in Saskatchewan, and they measured temperature greater than 125 degrees at just over 3.5 kilometers below the surface. And that drill cost about 3.7 million. They drilled another 4 test wells, and likewise, back in 2019, they also received a grant from NRCan, and they've got investors lined up. So they're plugging ahead, and everything looks promising. They're hoping for completion in 2023. So this could potentially be Canada's first full-scale geothermal power plant providing electricity to the grid. Like Alberta number 1, they will be using a binary cycle power plant with 3 wells bringing hot water from depth, running a turbine with a working fluid, and then pumping two wells to pump cool water back into the earth. And again, like Alberta number 1, they are also planning some direct use heating projects. Their power plant is intended to be 20 megawatts, so a bit bigger than the Alberta #1. And they also own the rights to develop up to 5. So if the first one goes well, they could develop up to 4 more. So that's very exciting. Terrapin and Deep are both female-led Canadian companies. Dr. Catherine Hickson is the CEO of Terrapin, and Kirsten Marcia is the CEO of Deep. They're both registered professional geoscientists that were educated in Western Canada. The third project that I wanted to mention is in northern BC, just south of Fort Nelson. And this project plans to utilize a depleted natural gas reservoir. And they're hoping to begin drilling this summer. Hot water, based on the existing data, they expect to be able to get hot water, that same 120-degree target, but shallower than the other 2 projects, probably at only 2 to 2.5 kilometers depth. Like the other 2, they will use a binary cycle power plant. Initially, it'll be a 5 megawatt capacity. If it goes well, they have a plan to expand it to a 15 megawatt facility. And they hope to be operating by the end of 2024. Back in March, they got 40 million in funding from NRCan. So you can see that the federal government is very interested in geothermal, and they're investing in this. So that's very exciting. The Clark Lake geothermal project is 100% owned by the Fort Nelson First Nation and Saulteaux First Nation. I just wanted to finish off with a quote from Charlene Gale, who is the chief of the Fort Nelson First Nation. And she says, "We are creating an economy that not only recognizes our current needs, but one that looks 7 generations into the future." And I just like that quote, and I think it's a good way forward in Canada. So a quick summary of these 3 projects. The Clark Lake project has the higher geothermal gradient. That's why they don't have to drill as deep to get that required temperature. Alberta #1 and Deep require a bit deeper drilling, but still economic. But all 3 of these projects are within the Western Canada Sedimentary Basin, and they all use binary cycle power plants, slightly different capacities. They all have similar target of 120 plus degrees. The main difference is how deep they have to drill to get to that temperature. Deep is hoping to be up and running in early 2023. If that's the case, it's likely to be the first geothermal power plant in Canada. Alberta #1 will hopefully get up and running in 2023 or 2024, which would make it the first in Alberta. And then perhaps by the end of 2024, we would also have one in BC. So that ends the first half of my presentation, or maybe slightly more than half. And so we can take a break if there's any questions.
Wonderful. We definitely have some questions. Anyone who does have questions at the moment, you can put them in the chat. Let us know, and I will ask those for you. The first question that I was sent was, how efficient is geothermal as an energy source? What percentage of the heat is captured versus lost in the process?
I mean, the water isn't cooled down. Like, it's hard to, like, if you measure the BTUs of the hot water, you're not going to get that all, because you're not sending, when you send the water back into the earth, it's not like freezing cold. It's still warm. But that's why you keep pumping up more water, and you keep putting water back into the earth. And so a geothermal power plant, if it's done right, it can keep going for decades and decades, because the water will keep getting warmed up by the rocks. So in that respect, it's quite efficient. It also has a very small footprint on the surface of the Earth, which is appealing. And it has a low carbon footprint.
Absolutely. That actually relates to one of my questions is what kind of upkeep is required for these geothermal power plants and how long is their lifespan? We talk about oil and gas having a certain lifespan, even renewable energy has a certain lifespan. How long does a geothermal plant last?
Yeah, I mean, I'm not an expert in this, but definitely a few decades is not unreasonable. With maintenance to the plant and a sufficient resource at depth, I'm sure you could push that a longer, but certainly a few decades. And as far as upkeep, you do need to worry about like the hot water that you're pumping up isn't pure water. It has salts and minerals, and so you do need to get those minerals and salts out of the water, or else you'll have scale building up on your pipes and stuff. But it can also be a bonus because some of those minerals in the water might be valuable. So I know that at least in Germany and I'm sure other places, there are geothermal power plants where the water has, say, lithium in it, and they actually filter out the lithium as like a little side revenue stream.
That's awesome. Getting revenue from a lot of different sources, getting resources from many different places. We have tons of questions in the chat. Thank you everyone for these questions. The first one is for the binary cycle geothermal plants. What is the secondary fluid that is used and does it have potential environmental impacts?
So as far as I know, at least the Alberta #1 is using something called an organic Rankine cycle engine. So the secondary fluid is I don't know the exact chemical makeup, but it's like an organic fluid. As far as the environmental impacts of that fluid, it should be a closed loop. Like you can keep reusing that fluid, I believe. Perhaps there's a little bit of loss, but that I've heard of, there's not. I don't think there's any huge drawbacks to using a secondary fluid.
Okay. Cynthia wants to know, why has it taken Canada, I believe, so long to do this type of heating?
That's a good question. There was a lot of interest in geothermal back in the 80s when during the oil crisis, and the federal government launched the National Energy Program, but then when oil and gas bounced back, they kind of just put that all on hold. So I would say that mostly it's due to politics and the fact that Canada has a lot of oil and gas resources. But again, that's not my specialty, but it's complicated, I think. Yeah,
there's definitely a lot of different aspects that play a role. Kevin wants to know what flow rates are required for 120 degrees Celsius wells to generate power.
I don't know the numbers off the top of my head for flow rate, but I do know that geothermal wells are bigger than oil and gas wells. Like you're not looking at a 4-inch well or something like that. Each of these wells is going to be probably like 10 or 12 inches in diameter, and you're going to have 3 of them pumping water up. But as far as like how much they're pumping up, I don't have those numbers, but it is quite significant.
Yeah, quite substantial with pipelines that big. So does that mean it's not possible to use, for example, all the abandoned, the orphan wells in geothermal? The pipelines are just, or the wells are just too small?
They're too small. There is some talk of using them for like small district heating projects, but yeah, you would never get the flow rates required for electricity generation out of an oil and gas well.
Okay. Nathan wants to know, what is the permeability between a draw well and an injection well? Do you anticipate loss of water in the system?
Yeah, and so to make one of these like conventional geothermal power plants economic, you do need high permeability and porosity in between the, the the production wells and the injection wells. There is something called enhanced geothermal, EGS, where you hydrofrack the rock, and so you can use fracking to increase the permeability in between the wells.
Okay. What impacts the geothermal potential, that gradient that we saw? What are some of the factors that can play a role in whether it's that steep line or less or more steep?
Yeah. So a big part of it is that radioactivity. So the rocks, if the rocks have a lot of uranium, thorium, and potassium, the rocks are going to be hotter. Also, if the rocks are younger, so near to a plate boundary, or near to a volcano. So the reason why Iceland and New Zealand are great for geothermal is because they're both on plate boundaries. Same with Ethiopia in the African Rift. And then the reason why Mount Meteor has a high gradient is because it's on a volcano.
Okay. What are some of the downsides of geothermal energy besides the expensive setup?
So there's like obviously the expense of drilling. The margins are low, so you can't. You really need to do your research, and like in oil and gas, you can afford to drill a dry well every once in a while, because you have the margins. In geothermal, you really need to do your research and know where you're drilling. You can't afford to just drill a bunch of holes and come up with nothing. Yeah, I mean there is infrastructure at the surface, and yeah, I mean that's what comes off the top of my head.
Yeah, that real high initial cost and that cost for setup is definitely the biggest challenge.
Yeah.
Deep Earth has rights to 5,000 hectares. Do most projects have such a large surface footprint?
I don't think so. I think they wanted to make sure they had lots of room for expansion. So yeah, they could do 5 20 megawatt power plants. So 100 megawatts is fairly significant. Yeah, I'm not sure how many hectares Alberta #1 has the rights to, for example.
Okay, and last question for now. Thank you everyone for all the amazing questions. There's just so many. If I've missed anything, please let me know. So the last question for this first part, how is the soil temperature impacted by long-term operation? Is there a degradation of the soil due to the movement of that hot water up through the soil?
I don't think so. There are other researchers at Future Energy Systems that study stuff like this, but because these wells are deep, you're looking at 2, 3, 4 kilometers. It shouldn't affect the soil too much. Like the upper, you're talking about tens of meters, hundreds of meters. It's quite far away from the reservoir that you're drawing from. But there are people that do modeling, and they do look at the temperature of the surrounding area over years and decades. So that is definitely something that these companies will look at.
Another one of those things that is just a question that's remaining in a new kind of energy source that we need to look at. Awesome. Thank you so much, Cedar. And thank you everyone for all the questions. There will be time for more at the end, so keep popping them in the chat, and I'm going to hand it back over to you.
Okay, thank you very much, everyone. So we'll move on to the second part of the talk, geophysics. And what is it? So how can we look inside of the Earth other than digging holes and drilling wells? Well, you can use physics and technology, and I'll talk about how we do that. So if we understand the physics that is going on underground, then we can use math to interpret measurements that scientists make at the surface of the Earth. For example, if you know that different rocks have different densities, you can use gravity to make inferences about what that density distribution is. Likewise, if you know how sound waves propagate through different types of rocks, you can use seismic to image the subsurface. And likewise, if you know how radio waves interact with the Earth and interact with different types of rocks, then you can use radio waves to image the subsurface. And that is what I do in my research. So what are radio waves? Radio waves are electromagnetic waves with very low frequencies. So this is the electromagnetic spectrum. Radio waves are the lowest frequency. Then you have microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. So yeah, so I'm using these very low frequency electromagnetic waves to image the rocks inside the Earth. And just a little aside about radio waves. So radio waves have a large range of frequencies, and they're used for all kinds of things in our day-to-day lives. So your Wi-Fi router at home probably operates at 2.4 gigahertz or 5 gigahertz. And your FM radio would operate in what they call the very high frequency radio band. Your AM radio would operate in the medium frequency band. And so the research that I do uses radio waves that are way down here. It's called Magnetotellurics, or MT, and it uses very low frequency radio waves all the way past anything that we use for communication. Down here, the only things that humans use this for is submarine communications. You know, your normal person in their day-to-day lives would only ever use kind of these frequencies here. And a little fun fact that I like to show when I'm talking about radio waves is the difference between different radio types of radio station. So for example, if you're listening to CBC Radio 1 in Edmonton, you can listen on your FM radio or your AM radio. And FM stands for frequency modulated, where the frequency is 93.9 million hertz, but the frequency can vary, and that's how you get your radio signal. Whereas if you're on the AM dial, it's amplitude modulated, and your frequency is fixed at 740,000 hertz, but the amplitude of the signal can change. So just a little aside. So my geophysical method, Magnetotellurics, uses naturally occurring radio waves, and I use these to measure the electrical conductivity of the Earth. And so high frequency radio waves, and by that I mean high frequency when it comes to MT, that are about 1 to 1,000 hertz, are caused by global lightning activity, which is happening all the time, all over the planet. And then the low frequency radio waves from microhertz to 1 hertz, so lower frequency than even the submarine communications. These ones are caused by space weather interacting with the Earth's magnetic field. And so these high frequency lightning signals image the shallow structure of the Earth from hundreds of meters down to kilometers. And then these low frequency space weather signals image the deep Earth from tens of kilometers down to hundreds of kilometers. So right into the mantle, right through the crust and into the mantle. An MT instrument measures the electric and magnetic fields at the surface of the Earth. So it's basically a giant radio receiver. And the ratio between electric and magnetic fields is what gives you the conductivity of the Earth. And so that's what I'm interested in my research. And MT is used in geothermal because electrical conductivity is sensitive to the presence of fluids such as water and magma, and also clays, which are present in hydrothermal systems and are highly electrically conductive. One kind of silly thing about geophysicists is they don't like to talk about conductivity. They like to talk about resistivity, which is just the opposite of conductivity. So when I show my model, we'll actually be looking at resistivity, which is just 1 divided by conductivity. So we'll go back to this, this figure that I showed at the beginning, and we'll go to my study area. The Mount Meager region drew attention in the 1970s as a geothermal target because of 2 hot spring systems, the Meager Creek Springs, which was a popular tourist destination for a while, and the Pebble Creek Spring. And as I mentioned during the first Q&A, research was put on hold in the mid-80s, basically when the National Energy Program was shelved in 1985. The most recent eruption at Mount Meager was about 2,400 years ago, and drilling has found temperatures greater than 200 degrees at depths about 1 kilometer. So if you remember those projects I was talking about in the Western Canada Sedimentary Basin, this is quite a bit hotter, quite a bit shallower. Canada's largest ever recorded landslide, and it still holds this record, occurred in 2010 at Mount Meager. So while the temperatures might be promising, there are other hazards to take into account when you're working in an area like this. That being said, there's been a lot of renewed interest in geothermal energy in Canada over the past few years, and this has led to an influx of funding, and a new multidisciplinary research program was launched, which includes magnetotellurics, but as well as seismic and gravity and geologic mapping and chemistry and stuff. So this is what I'm part of, and I did MT fieldwork in 2019 and 2020 at Mount Meager. So this is a map of the Mount Meager area. These yellow dots are hot springs. So in 1982, some magnetotelluric data was collected along Meager Creek, and this showed that there was like promise of a geothermal resource there. But then, like I said, in 1985, people kind of forgot about it for a bit. And then in 2000, interest kind of peaked up again, and they did another survey on the south flank of the volcano, and again showed that there was potential there. Nothing really happened, and then we went back in 2019 and 2020, and I collected data at all of these red dots. So as you can see, what I was looking at was doing a very large scale regional study to try and image the deep structure of the volcano, like the magma beneath the volcano, and any pathways for heat to get from depth to the surface. So the actual Mount Meager Peak is up here in the north, and this is what it looked like back in August 2020. There's a glacier down the side of it, which I got a nice photo of from a helicopter. You can see the shadow here. And here's Job Glacier. So west of Mount Meager, this area here is filled with the glacier. So this photo, we're in a helicopter over here looking at this ridge this ridgeline here. And so through the Job Glacier, there are 3 fumaroles. So one here, and then another 2 here and here. So what these are is these are places where volcanic gases and heat have melted through the Job Glacier, and they're venting volcanic gases into the atmosphere here. So even though it's been 2,400 years since the last eruption, this is kind of evidence that there's still something going on down there. That's not to say there's going to be an eruption, but that's something that we're studying and something that will be taken into account for a geothermal power plant in the area. And then this is Pylon Peak, so just on the north side of the geothermal kind of prospect area. I just wanted to show this one because it's one of the most visually striking peaks in the area, and I was lucky enough to fly around that whole area in a helicopter for a couple summers. So this was my my field transport for a couple summers, and yeah, just another one of it flying in front of a glacier here. So, oh yeah, and the pilots were absolutely fabulous. So I just wanted to give them a little plug. If you're ever in Whistler and want to treat yourself to an adventure, yeah, they're absolutely fabulous. So how do you get a model from data, from geophysical data? So you do that by using a process called geophysical inversion. And because we're not interested in modeling every grain of sand and every drop of water, the first step is to take your study area and cut it up into a bunch of like blocks. Basically, you're as if you were trying to make a model of a volcano out of Lego. And so I took my study area and I chopped it into little Lego blocks, well, big Lego blocks, I guess. They were 250 meters by 250 meters and 50 meters thick, with some bigger blocks around the edges. But anyway, so I chopped my study area into this Lego structure with more than 2 million blocks. And then in a perfect world, you'd have some X-ray glasses and you'd just be able to look in and figure out what the properties of all those Lego blocks were. And there you go, right? Like what's the structure of the Earth down there? You'd have that. But of course we can't do that. But if you could take the Earth structure and add some physics to it, and then you could predict what data would be measured at each one of these red dots. And so what if you don't know what the Earth looks like underground? All you have is some data. You go out in a helicopter and you measure data at all these red dots. How do you get to a resistivity model from that? So you go back to your physics and you use that to predict basically what the Earth looks like based on that. So this little cartoon down here, data plus physics equals model, that is geophysical inversion, and that's what I did to make my model. So this is my resistivity model of Mount Meager. And as I mentioned before, we like to talk about resistivity. So red is low resistivity, but that's the exact same as saying that it's high conductivity. And so near the surface, there's all this high conductivity. And that's because there's hydrothermally altered rocks from hot water flowing through porous rocks, and it makes them conductive. And also there's salty water in geothermal reservoirs. So this is this is basically the hydrothermal system, and it's very conductive. And if we go down to sea level, it's not quite as conductive as near the surface, but still more so than the surrounding area. And that's because the hydrothermal systems extend for several kilometers. And so you're still seeing below Mount Meager and the fumaroles, all of this increased conductivity. And then if you go down a bit deeper, you see that it's still conductive around Mount Meager and the fumaroles. And so these are the pathways that are bringing, like related to the hydrothermal systems, bringing hot water to the surface and stuff. And then if we go down in the model to like 8 or 9 kilometers below the surface, there's this large, very conductive body. And what this is a magma chamber. So these are partly melted rocks, probably with some salt water mixed in. But this is basically the magma chamber that's feeding this volcanic system. If we look at some slices from west to east, you can see that magma chamber, and then you can see hydrothermal systems reaching up towards Mount Meager and the fumaroles. There's also a couple interesting features. If you recall, the known hot springs are down here along Meager Creek. There's potentially a hydrothermal system reaching up towards Meager Creek and another reaching up towards Fish Creek, but these are not associated with any known hot springs. So these are either old hydrothermal systems that are no longer active, or they're hydrothermal systems without surface hot springs. So this is something we're going to look at in our ongoing research. And then just a few more slices going from south to north. We see again the hydrothermal systems reaching up towards Mount Meager and the fumaroles. We also see this shallow, the altered rocks and hot water associated with some near surface geothermal systems. And we will quickly zoom in to this area because if you recall the southern slope past Pylon Peak, that's where all of the geothermal research in the 80s and for the past few decades has been focused. So this conductor coming up towards Meager Creek, that's associated with the hydrothermal system, and that's where temperatures of 200 degrees have been proven at 1 kilometer. But to reduce the risk of investment, we want to have as clear of a picture as possible. So in addition to my research, there's another group led by Dr. Jim Craven at NRCan, and along with his PhD student, Fatima, who's jointly working at Carleton University and NRCan. They took higher frequency measurements called audio magnetotellurics, and this is sensitive to even shallower structure. And so this is a preliminary model that she sent to me. And I guess I should say that even my model is not 100% yet. We're still working on it. But it's interesting to see that the data was collected separately. The data was processed separately. The inversion, the geophysical inversion was done separately. But we still see this coarse feature in my model is correlated with this detailed feature in their model. So moving forward, once we're both happy with our models, we'll collaborate and we'll get the seismic people and the gravity people and the geology people we'll all collaborate and come up with the best picture that we can of this resource. And then when it's time to develop, it'll decrease the risk of investment. So the rights to develop the Meager Creek geothermal resource are owned by Meager Creek Development Corporation, and they actually intend to generate green hydrogen instead of sending electricity to the grid. So this company is run by a couple companies called Well Done, and then an Alberta company called Remedy Energy, who has decades of drilling experience in Alberta and elsewhere. So these two companies came together to form Terrador Energy, And so their plan is to develop green hydrogen from geothermal energy at Mount Meager. I don't know a lot about hydrogen, so I'm just going to take a couple minutes to talk about a few figures from this report that NRCan released at the end of last year. So hydrogen is used for fuel and heating and fertilizer, among other things. And so it's a necessary energy source, or a good energy source for the future. You can generate hydrogen from methane from fossil fuels, and we call that blue or gray hydrogen. We're interested in green hydrogen. So this is when you split water into hydrogen and oxygen using electricity from renewable sources such as hydroelectricity, wind, or solar. And I'm going to add in or geothermal. NRCan did not put this in, but it is a great idea. So one of the big advantages of green hydrogen is that it's the lowest carbon of these hydrogen sources. The con is that it's expense. It's the highest cost out of these sources. The nice thing about Terrador's plan at Mount Meager is they're going to pump up hot water to create electricity for the electrolysis, but then they'll use a little bit of that water as actually the feedstock for the hydrogen reaction. And because the water is already hot, it actually reduces the cost of the project. So a great innovation, and I'm looking forward to seeing what happens with that. Currently, the world's largest green hydrogen plant is in Canada. It's in Quebec, and they're using hydroelectricity to make the hydrogen. So this would be the first one that uses geothermal. So that's very exciting. I wanted to quickly mention the Alberta's Quest project, a blue hydrogen project, just because it's close to home, and you may not have heard of it. So this is a project operated by Shell as part of the Athabasca oil sands project. And so they're creating blue hydrogen in Fort Saskatchewan, which is, if you don't know, it's just northeast of Edmonton. What might the Canadian energy sector look like in 2050, at least according to that NRCan report? Several projections show a dramatic increased demand for hydrogen over the next few decades. Currently, Canada's secondary energy demand is predominantly natural gas and liquid fossil fuels. By 2050, NRCan projects that could shift more towards electricity and hydrogen, and geothermal could play a role in both of these slices of the pie. So we're down here in laying the foundations for a hydrogen economy for the future. And I would say that on this innovation step, Terrador is really stepping it forward by using geothermal and hot water to do this green hydrogen. And if I could be so bold, I would say that research in general, and hopefully my research is helping to de-risk investments, because, like I said before, geothermal projects, yeah, you really need to understand the ground. So that's where us scientists come in. I would like to thank Future Energy Systems for funding my research, and to Valerie for arranging this talk. My PhD supervisor, Dr. Martin Unsworth. This pretty slide template I got, so I'll give them some credit. Additional funding from NRCan and Geoscience BC. Geophysical inversion is very uses a lot of computer resources, so I run my inversions on a large parallel computing cluster, and that resource is donated by Compute Canada. And then I would also like to thank Dr. Steve Grasby. He's overseeing the multidisciplinary project at Mount Meager over the past couple of years. We do have some more time for questions, but I also wanted to point out that you can always connect with me via email, Twitter, or LinkedIn. But yeah, I can take your questions now.
Wonderful, Cedar. Thank you so much. You can't see anyone else, but I will give a wild round of applause. Everyone else can do it on their mute button, use the emojis. That was fascinating. There was a comment in the chat you probably didn't see, but Joel wants to know how they can get this kind of work, right? When you were showing all of those amazing photos. So amazing photos. I had one question before I get into all of the audience questions, which there are many of. Do you recommend doing this kind of assessment, your kind of work, for every geothermal project, or is that feasible?
It's very common. Like in a place like Iceland or New Zealand, they have MT data over pretty much all of their geothermal resources.
Okay, so it's something that we're gonna definitely be doing a lot more of.
I mean, other than the helicopter, it's a lot cheaper than drilling holes.
Definitely. So someone wanted to know, you mentioned really early on that there was a 12-kilometer well, and they were just wondering, what is that well for? Is it for geothermal?
No, that was just for science. You can look it up. I think it's just called the ultra deep well, or the super deep well. It was in Russia, I believe. But they were basically just trying to drill as deep as they could drill.
Was the Earth race versus the space race.
Yeah,
basically.
exactly. So yeah, if you just Google super deep well.
There you go. We'll go Journey to the Center of the Earth, but real life.
Yeah.
This is science fiction in real life. So the next question was, is it possible to use an active source of radio waves instead of environmental EM energy for the MT method?
Yeah, so it's called a controlled source MT, so CSMT, or if you're doing AMT, it's CSAMT. But yeah, you definitely can. The problem is, if you remember when I showed the radio wave spectrum, you had your Wi-Fi and your FM and your AM, and there's also stuff like aviation communications and military communications, and there's very strict rules about which frequencies you're allowed to broadcast. You can't just go on and set up a huge antenna to do MT and interfere with airlines and military.
That would definitely be bad. Don't go out and do that. Anyone who's wanting to do this work. The next question is, how do you usually build the initial models for MT inversions? Do you use information from other geophysical methods?
Yeah, so you can either start. So my model, because it's like just kind of the first stage, I started from a uniform model. So all of those Lego blocks, they're all the same. And then you get the computer to generate model after model after model. And so I think the model I showed was, after like a few hundred iterations of these Lego blocks getting just changed incrementally until the predicted data is as close to the real data as possible, while still being geologically kind of feasible. But long term, I want to tie in the seismic and gravity information as well. So you definitely can do that. You can also throw in faults, structure in the rock from the geological mapping. So yeah, you can do both. You can start from a uniform model, or you can start from a model that you got from a geologist or another geophysicist.
Okay, awesome. Cassidy, I know you got sent a question.
Yeah, Danielle's wondering if you can speak more to NRCan, which was Natural Resources Canada.
In which way? Like,
Daniela, feel free to, if you've got more details or have specifics, but was just asking generally if you can speak more to it. And maybe while I'm waiting to see if Daniela has more details on what they're wondering about, they were also wondering if these slides would be available. Of course, a replay of this talk will be available on the Future Energy Systems YouTube.
Yeah, I'll just have to double check with my supervisor and my funders.
Absolutely.
So I do have some more details. So just if you can speak to the purpose and goals.
From NRCan?
Yeah.
Yeah, so I can't remember the name of the initiative, but the money, the grants that were given to Alberta number 1 and DEEP in 2019, they were part of the same initiative. I mean, maybe it was just called the Renewable Energy Initiative or something. But the federal government, as part of their net zero by 2050 commitment, they were pumping a bunch of money into all kinds of renewables, wind and solar and tidal and everything, including geothermal. So yeah, so NRCan, in addition to doing lots of great research, they also provide a lot of funding to these startups and to university researchers.
Wonderful.
Thank you. I did pop a link if you want to poke at their website on the Government of Canada page if you just are curious. It looks like it's a pretty good resource.
And I guess I should also say, just as far as public resources, if you're interested in energy in general, they have tons of statistics and graphs and pie charts about energy usage in Canada and electricity generation, broken down by province, broken down by type. Yeah, there's a lot of great public information on their websites.
Great resource to use. Awesome. Thank you for that question. The next one, I'm going to do my best, Maria. I'm assuming that you got your I'm not going to say that word correctly. Resistivity model from an unconstrained inversion. Is that correct?
Yeah.
Oh, sorry.
Oh, sorry. There was more.
In that case, do you think that using the structural interpretation to constrain the inversion would provide a more accurate image of the geothermal system? That was quite a question, Maria.
Yeah. So yeah, mine was unconstrained. It just started from a uniform half space with topography included, and the AMT group might use my model to constrain their inversion, and long term we're hoping to do some joint inversions between the MT and the gravity, perhaps, or at the very least use them to constrain each other. Because mine is deep, the bedrock geology and the fracture analysis wouldn't be quite as relevant as they would be to the AMT group. But yes, all of the groups are collaborating. We're all going to put our models into Leapfrog Geothermal, and yeah, hopefully bounce it all around and come up with a more unified model.
Okay. Another question we got was about Mount Meager. Is it a better candidate for geothermal energy because of its more recent eruptions?
Yeah, so because there was an eruption 2,400 years ago, rocks take a long time to cool down. So if there was melted rocks 2,400 years ago coming to the surface, there's probably melted rocks today, and certainly that's what my model would suggest. And so there's still a lot of heat.
Okay, and another technical question. Is seismic useful to characterize the geothermal system, or is the P wave velocity not so responsive to temperature changes in the rocks?
Probably shear wave velocity is more relevant. Again, I'm not a seismologist, but there was a passive seismic survey done at Mount Meager, as well as a distributed acoustic array. distributed acoustic system. And that's done by a group at the University of Calgary, Hirsch Gilbert and Jan Detmer. So yeah, so they're, I'm not sure how they're doing with their research currently, but yeah, so there is seismic being analyzed there. And I certainly the shear wave velocity would be sensitive to fluids such as magma and water.
Okay. A question going back to that Clark Lake project. I'm not sure if you've looked at this or considered this when you were reading about it, but what leverage allowed the two First Nations groups to obtain an ownership interest in the project?
Well, yeah, I don't know the details. I would guess that it's on their land. I haven't been to Fort Nelson. I'm supposed to be going up there this summer to do some MT in the Clark Lake area, and I will try and find out.
We'll just have to have you back in the future to report on all the amazing things you found. All right, are there any last questions from the audience? Pop them in the chat. Let us know. We will stick around for a couple minutes at the end, so if you've got a burning question, you just don't feel comfortable asking it in the space, we will be around so you can ask it. One last question that we got was, did the survey site change between 1985 when the first wave of research closed down, or is it the same area 20 some odd years later, 30 years later?
Let me see if I can go back. It's pretty much the same area.
It's always so many more slides back than you think it is.
So yeah, so in 1982, it was along the creek, and that's because that's where you could get to in a truck. And then in 2000, they extended it up the south slope because they had a helicopter. And this is where a lot of the research was done in 2019 and 2020. My group took it a bit further because we were interested in the deep structure. But yeah, basically the south slope of the Mount Meager Massif has been the predominant research area for the past like 4 decades.
Perfect. All right, last question. Joel wants to know, as an undergraduate, how can I do this kind of work? Do you have any advice?
Yeah, go into geophysics. In 2019, we took an undergrad with us to collect a bunch of this data. So he got to fly around in the helicopter with us. And then in 2020, it was me and my supervisor and another grad student. So yeah, like keen undergrads in geophysics can get involved. And then if you want to pursue graduate studies after you get your undergrad, then that's definitely a good option.
Absolutely. I think flying around in a helicopter was probably my favorite part of my graduate work as well. It's a lot of fun. But thank you again, Cedar. This was an amazing talk. Another wild round of applause.
Hey, thanks for having me.
It was so much fun to learn. Thank you everyone for joining us on this Wednesday evening. We hope that you will join us again next month on June 23rd at 7 p.m. We are going to be talking about developing sustainable urban infrastructure from research to practice. So the grid, electric vehicles, smart buildings, all of it. So please join us. It should be a really interesting evening. As I said, we will stick around for a couple minutes. If you do have those questions you didn't get answered, please stay around. Thank you again, Cedar, and Cassidy, I'm going to pass it to you.
Thank you so much, Valerie, and I'll echo again, thank you, Cedar, for sharing your time and your work and your expertise with us. Yes, please do register for next month. I also put a very brief survey into the chat and I'll be emailing it to you as well. If you have any feedback, topics you might like to see, that's a great place for us to capture that. We want to know what you want to know about. So I think that's all I have to say. Thank you again. It is a beautiful evening in Edmonton. So if you are in Edmonton, I appreciate that you took the time to hang out with us this evening.
And thank you for everyone who's not in Edmonton. I saw in our chat, we had some people joining us from Mexico, from Bolivia. So thank you people from all over the world for joining us tonight. Have a wonderful evening.